sir.
Okay.
Good evening, dear participants. We welcome you all for this digital knowledge webinar session in aeronautical engineering. Today, our session will be in innovations in jet control. This evening, our speaker we have with us Dr. Dharmahinder Singh Chand from Chandigarh University. Is currently the professor and head at Chandigarh University, and is very well-known personality in teaching fraternity of Chennai and Tamil Nadu of aeronautical engineering. And is very jovial person, very approachable person, very friendly, and he is very well versed in speaking Tamil. He is very close to all. He really motivates students very well, and that's the reason we have him today. And before we go into this webinar, I request our head of department, Mr. Tanivel Murugan, to kindly convey the welcome address.
Yeah, it's a great evening for us today with our team. On behalf of JEC, our director, Dr. Regina JEPPIAAR, on behalf of our academics principal, Dr. V. Natarajan, we welcome our exclusive speaker on our aerospace domain, that is our Dr. Dharmahinder Singh sir. We used to call him Singh sir. Okay, that's a famous word that we used to circulate among our groups. And he is one of the hand-picking few eminent persons, those who are available in the aerospace domain. I cannot even say in Tamil Nadu, I can say even in India. So right now he's head of the department of Chandigarh University, and he's organizing a tremendous effort on organizing great opportunities with the aerospace domain with outside India. Right now also, before 2 days, we used to have exclusive seminars with SpaceX, and the same thing, we also expected continuous support from our exclusive speaker that is going to extend in our aerospace domain to be developed in future. So this is what our today we have a great effort to pick him up in his free time and to arrange a great seminar on the great topic called on jets. So today is going to deliver a very good topic on precise concept of jets concepts. So this will be a great inspiring session for the students, those who are going to be having a planning to pursue the MS, or having a planning to pursue their PG or whatever it might be related to propulsion, or they have a plan to propose for any conference or journal in future. This might be a key point where this fire inspiration is going to happen with them. So I kindly request everyone to be aware with this seminar session, and take away whatever the things he's going to share with us. This will be a great evening for us. I'll hereby once again welcome in behalf of students community of JEC and other participants on behalf of management. I welcome you, sir, and thanks for accepting our invitation in the short span of time and sharing this moment with us. Thank you, and welcome you once again.
ரொம்ப ரொம்ப நன்றி ப்ரொஃபசர் ரொம்ப நன்றி ப்ரொஃபசர் Amit and Professor Tanivel. As you said, yes. I can speak Tamil also, so thank you very much again. Yes. So today I have chosen this topic because this topic is very much popular nowadays in aerospace field. So my presentation will run like this. First I will give brief introduction, then what is actually mixing enhancement, and I have chosen passive control only because I will tell you elaborately. There are few controls also, but I have chosen for this presentation passive control. Then what are in passive control, what are the various control techniques. Then the research I did was on perforated tapes, so I am going to elaborate it, perforated tapes. And what was the discussion of these results I will be, and what was the outcome. So why we need this to control the jet? Because it is an active research area due to its vast application to improve the stealth capabilities, minimization of base, heating, reduction of acoustics, and all. Most of these applications require mixing enhancement of the jet from the surrounding, and because of this surrounding, we can mix with the jet, and it will be that mixing will be rapid. So to achieve this mixing, we need to have a small scale vortices to be introduced in the jet at the nozzle exit. This will be done in two ways, active and as a passive way. And these, so many researchers over a period of time, they have identified these. So when I will talk about active techniques, in active techniques we need external source, but when I will talk about the passive techniques, we don't need a, external source to execute this mixing enhancement. Now, among these two controls, passive control in the form of tab has become very popular because of simple geometry, efficient mixing performance capabilities. Tab geometries, I will be showing in upcoming slides these shapes and all, how we are introducing these shapes and what how we are attaching these tabs to the nozzle. So that in coming slides I will be showing you these arrangements also. Tab geometries such as rectangular, triangular, circular, arc, etc. have been studied extensively. However, among these solid tabs shed mixing promoting small vortices of uniform size only, but it will be beneficial if the mixing promoting vortices themselves possesses mixed size. So one, if one is vertex is small, another is large in size, then mixing enhancement will be better. So what are the different to generate such small scale mixed size typical tabs with perforation I have used with a flat place have been used. So I'm not, I will talk later to this. What are the mixing techniques? Actually, active control, like I told, pulse jets are there. Then these are used by the Bounder and Marinette in 1973. But I'm not going to passive active controls, I'm going to passive controls. So passive controls, we are having swillers. So swillers, actually mostly these are employed, I'm starting with the combustion chamber, later I will go to nozzle. But swiller, it is a stationary part, as you can see from the diagram. These tabs, these blades will, this actually, this is not rotating, this will be fixed, but because of the shape of these blades are vane, it will try to swill your flow, and once it is reaching to the combustion chamber, there we can mix fuel, air fuel mixture, we have a proper air fuel mixture, and combustion will be very smooth, and we can avoid the losses. Now we have a counter flow, and now I'm going to exit nozzle. So we have a counter flow, as you can see here. Here we are, this is the primary flow, and we are circulating this counter flow. It goes here and reduces it is mixing enhancement it enhances mixing enhancement property. Now you can see annular and co-annular jet, one jet is coming out of it, and this primary jet will come. Once they are coming out, they are mixing, and so this co-annular is surrounded with the main jet. Annular is surrounded by the co-annular jet here. So once they are coming to the atmosphere, so they will mix it with each other relatively. That upper one will be cooler one, and this will be the hotter one. So once they are mixing with each other, so this will enhance your this will enhance mixing properties, and it will control jet. As I told, why we need to control the jet, because once we control the jet, our stealth capability will be improved, because of we are restricting our infrared signatures. And once we are one more thing is that, and it will base heating will be reduced because of this cooling, this relatively cooled this and co-annular jet. Now the starting of this starts with the small tabs. It was started in the delta form of a delta tabs in 1992. So you can see at the nozzle exit, 4 delta tabs are attached. So these tabs, what they will do, they will try to introduce small water, because these are the flat plates. Flow is not there. Once they will, the flow is not behind the behind these tabs, so they will try to generate small vortices, and it will try to mix with the main flow. And once mixed flow is, it will entrain these vortices, and it will try to reduce its noise level and infrared signatures. Now, before tabs are introduced, there are so many also arrangements at the nozzle exit. The nozzle was made like a triangular shape. Instead of having a circular shape, they made as a triangular shape. So once this is a triangular shape, you can see three edges are there. These always edges are prone to produce the vortices. So because of this three edges, we are able to produce the vortices, and they are mixing with the main jet, and they will try to reduce this. So similar diamond shape also was tested by by Prodapali in 95 and Alvi et al. Also in 1995. So they also, in here you can see we had three um, uh, what is called three vortices here we are having, but here in this we are having four corners which provide more vortices compared to this. That's what they tested first. This, it was tested first triangular, then they tested diamond shape, so it produces four vortices at the four corners. Then S. Selangon and Radhakrishnan 1998, they also tested one nozzle. That nozzle shape at the exit was rectangular. Now you can see here four vortices, and if you have a notch here, you are introducing two more vortices here and two more vortices here. Now you have increased that vortices uh, um, magnitude of vortices also. So it, you can see here, this is the geometry. They will try to introduce four more vortices, and you are able to see these vortices will be mixing with the main jet and try to suppress the noise level. Also mixing enhancement will be more efficient. Now so many people, then they went for an elliptical nozzle also. Here the shape was rectangular, here it was the notch type. Now next step was to go for a not a circular one, elliptical, because reason of that was when you are having elliptical shape, once the vortices, this flow is coming out of it, the symmetry will be changing, because major axis will become minor axis and minor axis will become major axis. It will try to rotate. So because of this rotation, mixing enhancement will be there. Here you can see this is called axis switching. Axis switching will be there. Axis switching, as I told, major axis will become minor axis and minor axis become major axis in the process of once it is coming out of the nozzle and it is going into the atmosphere. So this axis switching will help us to mixing enhancement. If you see here, this was the shape of the nozzle, this was the, and we have got this is the nozzle shape at the exit. So this was the elliptical shape nozzle. So here, if once it is coming, once it is try to rotate, major axis will become minor axis and minor axis will become major axis. So it will try to, it will enhance the mixing enhancement, and we will be able to suppress the noise. There are so many lobed and castle nozzle, notched and grooved nozzle. I am going to show you that. See, these are the nozzle. We have castled nozzle here. You can see here the shape, and here these are the notches we have carved in the, and the notch and the grooves are carved in the nozzle. So these are also will produce, because we are first main aim is to make more and more corners. If we are able to make more and more corners and in the nozzle, we will be able to sharp corners. If we are able to make, we will be easily available to produce more vortices. Once we are able to produce more vortices, the mixing enhancement will be there. Once mixing enhancement will be there, we will be suppressing the noise, infrared signature, and stealth capability will be increased. Now the first aim was to vortex generator. Half delta was starting, we start in 1993. Then finally you can see here it is half delta. It also produces, because here they have given curvature for the smooth flow of a jet, and then it comes a splitter type of a plate. The plate was like this, it was attached like this. So they have divided, and or you can say they have bifurcated the exit flow into two halves. So once you are bifurcating, in the between there will be a the vertices will be created, and it will be interacting both sides, and it will try to enhance mixing, enhance capability of a flow. Now, first tab was introduced by the Bradbury and Cadam 1975. It was a wedge tape, and they did for the subsonic. Ahuja and Brown did same thing for supersonic and under expanded. So what this tab was capable, it was able to create two pair of vertices and counter rotating streamwise vortices it created. So once it created vortices, and these are the few scientists or the researchers who have used this tab and done the experiment. I can show you this. So some apart from the tab, there was they use some researchers, they use crosswire. As I'm going to show you these pictures also, how this crosswire and how these tabs were, these tabs, how different tabs were used so far, and this crosswire also will be used by this by Srijit and Radhakrishnan. Lowaraju also used this in 2008, and I'm going to show this also. These are the pictures also. Now you can see then Takama used flat plate to manipulate it become smaller, and what he did then, he carved this flat plate and it become an arc type. So Taniarsu used in 2008 arc tabs, and it was phased in and phased out. So that also created lot of vortices, but he did for subsonic jets. Now you can see here what are the different types of tabs used. This was the flat tab, triangular tab, corrugated tabs. This is again flat tab, those Takama used, and he then same uh, flat plate, he just curved it, and he used phase in and phase out. These are the triangular tabs, and they have corrugated here. One you can see here, he has the tab was semicircle. Here it is triangular. Here it is square, and the same now it's flat plate. Then it was a triangle. Then it was a trapezoidal. So these are the tabs which were used. Then after using this, one breakthrough came in the jet control, that was known as a Radhakrishnan limit. Zaman told in 1993 that for the same projected area, width of the tab is more effective in enhancing the mixing than its length. But when Raja Krishnan did on research on this, that he found that same projected area, length of the tab is more effective in enhancing the mixing than the width. So this was the breakthrough in this. Then keeping in this mind, I introduced, this was the first time in history somebody has used perforated tab to control the jet, because purpose of this was the flat tabs, they were blocking the blockage ratio was more, and they are reducing the thrust. To compensate that thrust, here we did a perforation. Through this perforation there were two things. One, we counted for the thrust loss, and we are able to create smaller vortices compared to bigger vortices, because literature says that if you have smaller vortices, that mixing enhancement capability will increase. Before that, I have not shown you the cross wires. These were the cross wires. You can see cross wires. Here it is at the right at the exit. Here it is away from the right. This was done from this cross wire was changed 1D, 2D. 1D, if you see, D is the exit area. So it was away from 1D. That means 1D. Then they have changed to 2D, 3D also. but this is right at the exit. This is it. Now I am going to perforated tab. Perforated tab. The thing is that we are counting for the thrust loss, as well as you can see here two limbs are there, because when we created I will show you in detail also. But these limbs were capable of creating small vortices. Once small vortices are created, because literature says that if small vortices are there, we are able, mixing enhancement capability is more efficient. So that is keeping in all those mind, we did this research. So our research was done in Madras Institute of Technology. So we had a setup, we had a storage tanks, we had first compressor, then we compressed and stored in storage tanks. Then this was our laboratory, and we did these experiments. Now I am going to, this was the we did for convergent nozzle only. That means the sonic and subsonic. Subsonic and sonic, and we went for under expanded level also. So once we did this, here was the attachment of a tabs. This was the tab arrangement as the nozzle exit. I will show you the picture also. So we tested here. These are the tabs we used. It was solid tab. It was 1.5 circulation, circular perforation. Then it was 2 mm. Then it was 2.5 mm. Then finally we changed our shape circular to elliptical also. So my ellipse was horizontal, major axis as a horizontal and minor axis as a vertical. Here we just change it. Minor axis was horizontal and major axis was vertical. So here, this is the tab arrangement. What we did, you can see here is the perforation. This was the nozzle at the nozzle. So this slot was given to adjust our tabs to up and down. So if I need more blockage area, mainly this we can use for solid tab also. So we have provided this for our perforated tab also. So to reduce our blockage ratio also can be adjusted with this slot. Now once we are doing our calculation, we should keep in mind that subsonic jets can be converted to Mach number using isentropic relation, because we assume there is no loss, no losses. But when we are testing for supersonic, we cannot convert this because there are shocks are there. Because of the shocks, the actual reading of our pitot is not that much, that which we are recording. There will be a losses. So for this, we will be taking in terms of Mach numbers in subsonic, and for the supersonic, it will be in terms of pressure only. Now, this was the mechanism. This was my X direction, Y direction, and Z direction. So, X direction was along the jet flow. These two directions was perpendicular to the 90 degree to the jet flow. Now, if I will see what was happening in this and what we done here, it was first we see we did the effect of perforation size on subsonic and sonic jets. So as I told, we have used convergent nozzle. It can produce either subsonic or sonic jet. So why I did this perforation, and we got, what was the result that I will tell you. If you see these vertices here, if I am having 1.5, both the vertices are the same size. If I am having 2 mm perforation, one vertex is big and one is relatively small. In 2.5, one is big, one is very small. So what is happening when we did this for uncontrolled jet without tab, then solid tab, 1.5 mm perforation, 2.2 mm perforation, 2.5. I can see, you see this length, more the noise level. But here you can see these, they have reduced. You can see solid tab always, but there is always thrust loss associated with. So we have discarded this, and this is among this. If you see 2 mm perforation was the better because it was decays faster. And here you can see at Mach 2 that potential core is reducing tremendously, because if you control the potential core, that means you can reduce the noise level. So why it was happening, we came to know, because here if you see one vortex is bigger and other one is small. So vortices are mixed size, because as we know, literature itself says, our previous research also says that if vortices are mixed size, then you can have better mixing, which was proven through this. It is not that we have done only Mark 3, we did for Mark 4. Again, the result was same. So my 7.5 blockage. So blockage was 7.5%, 2 mm perforation. So again we did for point 2, authenticate our results. So again the results was same, 2 mm perforation was the um, influential one. Then we went for Mark 1 also for sonic. Again 2 mm perforation was influential to produce more vortices, and in the controlling the potential core also. Now this was in the direction of x-axis. We did it for in the direction of y-axis as well as z-axis. You can see here it is eliminating here for 2 mm, here it is broadening for 2 mm. So we came to know that we have done for x point near field also, far field also. You can see xd at 0.4 mark, and up to 7 also we went x by d. That means my exit dia was 2140. We have done. Again, similar cases were done to authenticate our results. Again and again, we have repeated our experiment. So to be clear and ensure that 2 mm perforation is really good for all the Mach numbers. So whenever we test, every test and every Mach number, 2 mm perforation to be proved very influential in all the Mach numbers. Then we went for Mach 8, and it was proven to be that 2 mm. From the investigation, it was found that subsonic regime tab with 2 mm circular perforation is better mixing promoter among other two circular perforations, that is 1.5 mm and 2.5. Reason behind that was this only. So clear reason is here. I will show you that. What was the reason? Again, I'm going to that. Reason was this. Because of vortices here are mixed size, here similar size, here one vortice is almost not there, another vortice is very big. So this bigger vortices was eliminating at a very short span of a time. Here both the vortices are there, strength is same, but they are not able to fight with they are fighting with each other. While they are fighting with each other, they are not able to entrain that air from the atmosphere. So here these two are relatively different sizes, and they are able to entrap the air from the atmosphere. So once we did this, then we thought we will go for same for sonic jet at NPR. Once you can see me NPR is nothing but nozzle pressure ratio. So my settling chamber pressure was 3 bar, and if I will take outside, atmospheric pressure is 1 bar, so that becomes NPR is equal to 3 bar. Again, when I am testing here, you can see, if you zoom it, you can see other tabs are giving more, fluctuations are more there compared to 2 mm perforated tabs. But it was not that. We thought we can go for another NPR4 also. We went, and we are going for NPR4 again. We saw same pattern was repeating for NPR4, and that fluctuations were very less, because the more the fluctuation, that means that shocks are more the shocks are there, more the noise level are there. If fluctuation is controlled, that in previous subsonic, there is no, you can see there is no fluctuation because that is subsonic regime. But if you go to sonic regime, and now it is becoming towards the supersonic flow, and that's what shocks are in the shocks are prevailing in the jet. So more the shocks here, more the noise level is if you control these shocks, you can control and you can suppress the noise level. So we have done for subsonic jet NPR 3, NPR 4. Then we went for, we tested for the same thing in x direction, y direction. These are in the y direction. Here you can see I have used here p upon p naught, but if you see here, we have done here m upon mj, because reason I have stated that for subsonic we can use Mach number, for supersonic we cannot use here Mach number, because their shocks are there, losses are there. We cannot say that the pitot probe, which is sensing the pressure, is equivalent to that pressure which is in the upstream of the flow. So because shock will be there, so losses are there. So we will retain the pressure which was sensed by, same we will we cannot convert this in other means. We cannot convert these things into Mach number, because shocks are there, losses are there. That derivation is for isentropic flow. Here flow is no longer isentropic. Now same thing was continued for y direction, and here you can see same thing. Now we are having y direction and z direction. This is for solid tab. Again it confirms that, you can see this was the 2.5. Here if you see 2, it was these, again the fluctuation was less. Here you can see fluctuations are more in terms of this, and here also fluctuations are more. So the reason again behind that, same thing, vortices are of mixed size. Now if I will go through this, now effect of perforation shaped on subsonic nozzle. Once we did these, 2 mm was this. Now same area of 2 mm we converted into our elliptical, vertical, horizontal axis, and vertical and horizontal axis as a major axis, and same area we converted into our one more tab, that is called square shape. Also we use here. I can show you now the shapes again. What are the shapes we have used? These 3 shapes, these were the solid tab 1.5, it is 2 mm 2.5. Now we went for this shape, this is elliptical perforation, major axis horizontal, major axis is a horizontal, here major axis is a vertical. So here these are the one more shape we introduced, that was the square perforation. But area we tested, what was the area? If you see the area of this and area of these 3 was kept similar, so that we will have blockage ratio same. And now we will see that what is happening to the jet control. Here I can go, yes, yes. Now we tested, we started again from Mach 0.4. From all these shapes we took and tested. Now you cannot see here 1.5, 2.5, because they are discarded now. Now we are going for uncontrolled jet and solid tab. Again we have taken, so that it will be reference for us, because control jet we are not using any tab, uncontrolled jet we are not using any tab, so it cannot be taken as a reference. But in solid tab we are using tab, so it will be a reference point for us. That's what we have taken, otherwise it is also discarded. Now same 7.5 blockage you can see for circular, 2 mm. Now it is 2 mm. Area is blockage ratio is now same because the area, the perforation area is same. Now we tested these nozzles: circular, elliptical perforation, major axis horizontal, elliptical perforation, major axis vertical, and square perforation. Once we saw this, we are able to find that you can check here. This is the obvious solid tab, and here you can see this elliptical perforation, major axis vertical was the uh, is proving to be better in subsonic. Let us see again in what is happening in the mark point. Again you can see same, it is proven to be very influential, even though it is beating at some point of a time in a solid tab also. So that was very good result for us, and very boosting for our research also. Then again, when we go towards mark 8, again it is proving better, but it is starting deflecting. That reason I will tell you why it is happening. Again I went for sonic. Again it is, you can see this solid tab obviously, but here you can see in this regime again this elliptical perforation, major axis vertical is proven to be. Then we tested for similarly y and x axis. Again it is showing same results. So once we came to know that now this was the subsonic, again we went for the sonic jets. Again when we went for the sonic jet, the result changed very sharply. What was that? We came to know that square perforation is better mixing promoter in the sonic jet. When you are moving towards the supersonic flow, this you can see here, square perforation is better promote mixing promoter, and even shocks are very less. So reason behind that is because more the corners you introduce when you are operating in sonic or supersonic flow, it will has the tendency, as literatures are saying, it has the tendency that it will promote more mixing enhancement, more vortices which are promoting mixing enhancement, as it was said in the literatures also. So this was very, even if you see, it is far better than the solid tab also in the sonic region, because so here we are capable, we are able to now say that solid tab can be replaced with the perforated tab in supersonic or sonic regime to control the flow, to control the jet. So this was the breakthrough in our, for this we have applied for our patent also. So maybe this year it may get sanctioned by the grace of God. Again, if I will see, again the results were same in the far field as well as near field also. Now we have done ISO mark contours for the control solid tab also. Now you can see solid tab here at x.1, the near field, and this is also for mark 0.6. We have taken only one because already we know the result, but to authenticate again and again, you can see in this z direction at 0.1, and here if you see, now you can see these vertices here, you can see these vertices, no flow is there, no flow is there in the near field, and these are the vertices, you can see these are the vertices produced. Now if you see 1.2, 1.5 mm circular perforated near field, you can see here a vertices, and near here you can see vertices. Now if you go to 1.2, sorry, 2 mm, you can see the difference here, and you can see here it is a one vertices only, here you can see four vertices only. Now you can see the difference why 2 mm circular perforation was very influential. You can see here the vertices, and here you can see the vertices. It shows that here the vertices are mixed size, here vertices are not there. If you go again for the 2, there is nothing is there, no vertices are there. So because you see that vertices, as I told, one vertices was one vortex was bigger and one was a smaller in size, so it has eliminated very beginning itself, so there was no vortices to attract this to entrap this mass flow rate from the atmosphere. Now here, if you see elliptical perforation, because why I have chosen 1.6, why we have chosen here, we have chosen because at 0.6 this elliptical perforation tabs are more influential than our these tabs also. If you see here, you see these tabs. Now if you compare 2 mm, here also 4 vortices, here also 4 vortices, but if you see the vortices size, it is very small in size and it is very influential in NC. And zero point 0.6 we are able to get, so because it is enter to the sonic region, trying to enter the sonic region, you can see vortices are there. But apart from that, we have taken a shadowgraphy also for NPRs. So I am going to show this and shadowgraphy also. If you see uncontrolled jet, you can see here shock cells are very large in a cell. You can see one cell, second cell, third cell, fourth cell, then starting diminishing. Now if I will go to solid tab also, here also shock cells are there. They are very smaller in size compared to the compared to this. If I will go to 2 mm circular perforation, this is for NPR 4 we have taken, we have gone to up to 6 also. Now you can see, if you see solid tab, here you can see these are also there, but here you can see 4 cells, here it is 3 cells only we are able to see. So obviously solid tab is good in promoting, but the thing is that it is associated with the thrust loss also. Now if you see major axis along elliptical, again we are able to see 3 and 3.5 cell, and this was the same. But if you go to here solid tab square perforation, you can see 2 cells only you are able to see, because that is why I told in supersonic region square perforated tab can be replaced, solid tabs can be replaced by square perforation tab. Here there you are able to see 3 shock cells, here we are having 3. That means we have reduced our shock cells. Once we are controlling our shock cells by introducing tab, in this process we are able to control the noise level. Consequently, we are able to control the infrared signatures. We can improve our stealth capability. Stealth capability can be increased. So this, if I will go to now uncontrolled jet for NPR 6, you can see here very huge shock train. And if I will go to solid tab, shock cells are dimension size, but still it is, we can see the cell patches are also still present in the flow. Now if I will go to 2 mm, again the condition is same, cell patches are same, and but smaller in size compared to uncontrolled. Similar case, elliptical perforation also, here you are able to see these cell patches are there, but smaller size compared to the uncontrolled this. And if I will go to solid tab, you can see there you are able to see up to, you see here up to this we are able to see. But if you go to square perforated tab, you are not able to see beyond this. Here we are able to see up to this. Here 1, 2, 3, 4, 5 cells are there. We are able to see 7 or 8 cells. So again, it is proven that if you are going for a supersonic flow or sonic to supersonic flow, square perforated tab is more beneficial, even good, even better than the square solid tab. So we are having two things. One, we can reduce the thrust loss, as well as we are able to control our shock cells also. if we are able to control, again I'm saying, if we are able to control the shock cells, we are able to control the noise level. Once we are controlling the noise level, stealth capability will increase, our base heat will reduce, and if I am targeting some enemy, uh, uh, for targeting enemy, my noise level, noise cannot be here, so it is very beneficial to come. Other shapes also were introduced. Why we are concentrating on a tab? Because tab is a solid geometry. Very sorry, the tab is a very simple geometry. We can attach to the nozzle exit and execute our plan. But other things, we have to cut the nozzle, we have to grooving, cutting, and all. This will they may give better result also, but the system becomes very complicated. Even if geometry is same for our tab arrangement, geometry is same. Only thing, we need to attach our tab, that we will be able to achieve our plans also. So these are the solid tabs. So once I'm taking, this was the along the x-axis. Now if we will prove this, now if you see normal to the this solid tab, you see it has broadened, cell is expanded, because nozzle will try to bifabricate to this flow, and your shock cells in the direction, normal direction, will expand more. These shock cells are enlarged in the size in normal, you will get contraction in the x-axis, and you will be easily able to control this, our jet flow. Again, if you see elliptical, again these things, but I will go to square perforation. You can see here, it was so many cells were known, but if you see here, 1 and 2 cells only are known to, where 1 or 2 or 2.5 cells are known, means visible to us. So what was the outcome of this? Was for subsonic condition, tab with 2 circular perforation diameter is found to be better mixing promoter than 1.5 and 2 perforation diameter. The result shows that among the perforated tabs with different shapes, with circular, elliptical, square studied, the elliptical shape with vertical major axis vertical is best mixing promoter than the perforated tab in subsonic conditions. If you go, the orientation of elliptical perforation has strong influence on jet mixing. The one with major axis vertical proved to be better mixing promoter than the major axis horizontal, even though the aspect ratio L by B, means length of a tab and the breadth of the tab area were the same. The maximum core length, that what I told you there, the maximum core length reduction was 58.33, is was achieved with the tab of elliptical perforation, major axis vertical for Mach zero point 0.4, 61.9 with 2 circular perforation for Mach 0.6, and for the square perforation, it was, that's what I was told, when it is entering toward the sonic region or supersonic region, square perforation tab proves to be better in mixing enhancement, and it has a very good mixing enhancement capability. So that's what it when we are going from towards the sonic or supersonic regime, the square perforation is 50 with having the elliptical perforation major axis. Now for transonic jet, the square perforation is found to be better than the circular elliptical perforation in promoting the mixing. In other words, perforation with sharp corners is found to be a better mixing promoter than ones without sharp corners for sonic and are under expanded sonic jets, which are wave dominated. Another important aspect observed is that under expanded sonic jet, the tab with square perforation promotes mixing better than the solid tab. That's what our plot was showing. And here also I have shown in the outcome also this was our finding. So one patent is filed already, it is in process. We hope that this year we will be getting this patent. And I acknowledge my guide, Dr. S. Taniyasu, who is HOD, MIT, Chennai, Professor E. Radhakrishna, Professor IIT Kanpur, Dr. S. Ellen Mohan, Professor Bharat University. I thank MIT campus who has given me the opportunity to do this project and come up with good results. And I am very much thankful to the Chandigarh University also, whom I am associated with now, and I am thankful to JPR College management, professors, those who have invited me and given me the opportunity to deliver my lecture. I hope I have completed within the stipulated time. We can have some question answer also. Last but not least, I thank Almighty. That is we called Vaheguru and it is God. Thank you very much.
Thank you so much, sir. It was very nice. It was actually more deep into uh, research, and we really liked it, sir. There are so many new things for us, and I'm really happy to see so many professors have attended today's webinar. There are so many professors who have acknowledged. And there is one question, sir. One question.
Yes, I will be
Uh,
happy.
uh, could you suggest any research area or topic in jets? Someone who is interested in research to do
Yeah,
in
see,
jet.
I have done. I have done in subsonic. You can pursue same thing in supersonic also. Even you can change that perforation tab also. As I said, more corners can be involved to create more vortices. So you can have more corners. I have used 4 corners. You can use 5, 6 corners also
Okay,
in
sir.
the
There is
perforation
another.
also.
Thank you
Yes,
very much,
yes.
sir. There is another question. Where can we use notch type perforated tab?
Notch type. Notch type
Yes, sir.
perforation is not there. Notch type perforation. Notch type perforation tab.
Yes, sir.
No, notch is different and perforation is different. Notch is
Yes.
done on the nozzle and perforation is done on the tap.
Okay.
So they both are
Got it. Got it.
entirely different. They both are entirely different.
Okay. Thank you very much, sir. There were no so many questions. Very few questions
Yeah,
were
yeah.
there.
Yes, yes, yes.
Uh,
Definitely.
there was another request, sir. I have today because of time we started very fast. So there was a question like we didn't introduce you well. Very sorry for
No
that.
problem. No, it's no.
I would like to just
Always I think in Tamil Nadu, everyone knows me more than in my native.
yes, yes, sir. For the students, sir, I just like to briefly speak about you, sir.
Thank
For
you.
all the
Thank you.
participants who don't know Dr. Dharmendran Singh Chand, uh, he has completed his PhD in Anna University. Then he has done his both BE and ME in aeronautical engineering. Apart from that, he has been convener for so many national and international conferences. He was the secretary for Aeronautical Society of India for Chennai branch for 2 years. Currently, is the vice chairman for Aeronautical Society of India, Chennai branch. Then he was Anna University Syllabus Committee panel member. He was the question paper setter in Anna University. He was the valuation board chairman. Then he is a thesis evaluator for University of Petroleum and Energy Studies, Dehradun, Uttarakhand. He received Best Teacher Award, Best Paper Award. During his undergraduation, no, he got his great score also. A very good grade score he got. We were students then when we heard that. Uh, and apart from this, he has 15 journal publications. He has 20 international conferences, 32 national conferences he has participated in. He is member of 5 professional societies. This is very fast to speak about, sir. There are so many things to speak about him. Because I know him by person, I could say a few more things. He's a good cricketer and he is a very good hockey player. He has represented his school and college team. And he's a very humble person. He gets sometimes doubts. He asks whoever it is, this is the doubt I have in cricket, he'll come and ask. So on a personal level also, I know him. A so friendly person and he is approachable. currently is working as professor and head at Chandigarh University. He has 15 years of teaching experience. He worked as professor and head at Tagore Engineering College also. He also worked at Ganesh Institute in Chennai. This is about sir. Sir, there are a few more questions popping in, sir. If you would
Definitely,
like.
definitely. Yes, 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 yes. I will be very
Yes,
happy to answer.
yes, sir. Few questions were there, sir.
Yes.
One question was, what test can be done in triangular nozzle in high-speed jet?
Excuse me, I'm not able to hear.
Sir, what tests can be done in triangular nozzle in high-speed jets?
No, see, you can, if you are going for subsonic, you can just have a pitot probe and pressure transducer. You can measure the pressure and convert that pressure into, if you are in subsonic, convert that pressure using isentropic relation into Mach number and plot these. You can find easily how Mach is. Changing in x direction or along the flow, and similarly in the normal direction to the flow also you can change. This is subsonic. When you are in supersonic region, record the pressure, no need to convert, because as I told, this pressure when you are in supersonic or subsonic to supersonic, the pressure losses are there because you are it is privileged with the shocks. So because of the shocks, losses will be there. So no, you cannot convert this pressure into Mach number, because no longer it is isentropic flow. So pressure you can plot and you can get easily. You will come to know how much pressure you have controlled, and once you are controlling the pressure, that is directly proportional to the noise level. Pressure is controlled. Noise level is controlled.
Sir, another question, sir.
Yes, sir.
How the blockage and thrust loss is related?
See, nozzle exit. If you see the thrust equation, if you see, it is m dot a plus m dot f into exit velocity plus m dot a into va. Va is the free stream velocity plus pe minus pa, exit pressure minus ambient pressure into ae, exit area of the nozzle. So this exit area is directly proportional to now thrust. So once you reduce this area, if blockage is more, area is reduced. So thrust is lost. So if you compensate this through the perforation, you increase somewhat area. So you are increasing the thrust. So this is how thrust and exit area is related as a nozzle exit.
Sir, another question, sir.
Yes, sir. Yes, sir.
What kind of effect will we have if we use one tab and if we have more than two?
If we
What kind of
use
effect?
what, yes, if we have one tab, this is called thrust vectoring. So we need to maintain the flow symmetry also. We need to control flow. If you are not using two tabs, so if you have more than, see, if you are having one tab, you will be having thrust vectoring. We don't want thrust vectoring. We want to control our jet only, or noise suppression. If you use two tabs, symmetry is maintained. If you use more than two tabs, then again that what is called this blockage ratio comes into exit. Your exit velocity, your exit area will decrease. Thrust loss will be there. So it is
Another,
kept only two. Minimum two tabs has to be kept, because to maintain the flow symmetry. Otherwise, thrust vectoring will take place.
continuing to that, sir.
Yes,
Is
yes,
it
sir.
advisable to have a swivel type of tab?
Swiller type, yes, why not? If you are able to develop it, if you have an idea, it is better. You can have, why not? But you cannot use one tab. As I said, you have to use two tabs also to control the jet. One tab will give you thrust vectoring. Two tabs will give you jet control. More than two will give you more blockage ratio, and consequently thrust loss.
There is another question, sir. In case of
Yes, sir.
rocket engines,
Yes, sir.
how can we relate our innovation, sir?
No, in rocket we don't want to have this, but in rocket to reduce the base heating, we can use a tap. That's what I
Okay.
told. For the base heating, to reduce the base heating, we can use the tap. So it will entrap the air from the atmosphere and it will reduce the base heating. So that's what how we relate our rocket propulsion with these tabs.
So there is another question, sir.
Definitely.
I hope it is not out of our topic. Do you
No
think
problem.
artificial intelligence will be implemented in flight control system installed in drones?
It's, intelligent. What? I'm not able to understand it.
Do you think artificial intelligence will be implemented in flight control systems
Why
installed in
not? It
drones?
is who it is. Everything is possible. Nothing is impossible. Only thing is we can use. Why not?
I think you have attended so many questions, sir. Final question, sir.
Yes, yes,
Just popped
definitely.
up. Question is, sir, can we use these tabs in three-plane thrust vectoring engines?
Three plane? No, if you
Three-plane.
see, if I said, if you want to go for a thrust vectoring, you no need to bother about the symmetry, because you want to disturb the symmetry, then only you are able to achieve the thrust vectoring. But in jet control, our main is aim is not thrust vectoring. We need to maintain the symmetry and control the jet so that noise suppression will be achieved, stealth capability will be achieved. We will reduce the infrared signatures so that my stealth capability will improve. So if we are going for the thrust vectoring, no problem.
Sir, you have answered all the questions, sir. Thank you so much for your
Thank you.
patience, sir.
No problem.
So,
My pleasure. My pleasure.
with this, I think we have come to the end of our webinar, and I thank all
Thank
the
you.
participants for participating today and attending all our sessions. It is so nice to have you all, and thank you for your support.
If you have some feedback, you can share the feedback with me so that it will be helpful for me to enhance my skills also. I know I have
But
commented so many mistakes, but let me see that how it will help me for my improvement. I need that feedback from the faculty as well as the participants.
that is
That will
really
be
a humble
that is
gesture, sir.
that is always my demand.
That is so humble. That's a nice humble gesture. Definitely, I will share that feedback, sir. And
Thank
thank you
you.
so much, sir, for spending your
Thank
time and giving an opportunity
always
for us.
Always
And it was
welcome.
I
Thank you. Thank
really
you. Thank you.
hope,
Thank you, Amit, and thank you very much.
yeah, I hope the session would have been useful for all the participants. Thank you once again, and wish you all a happy stay at home.
Thank you.